then we still need to subtract 273. So we're going to But notice that we were able to change two conditions at the same time. We changed the pressure and the volume. So the whole premise on the laws is that you start with an initial set of conditions, and that sets the constant. And Avogadro was thinking, well, why don't we standardize that initial set of conditions? And so basically he started doing experiments, and he standardized his experiments to always a given set of conditions. So he set his pressure to 1 atmosphere, temperature to 0 degrees Celsius, which is 273 Kelvin, and he kept measuring 1 mole of a gas. Now, this pressure and temperature set of conditions are now known as STP, standard temperature and pressure. Keep in mind that they're arbitrarily set. Well, the pressure, that's atmospheric pressure. That's at sea level, but temperature could have been anything. He just decided basically to work under those conditions. And he fixed the amount at 1. So when he studied a whole series of gases under that set of conditions, he kept getting the same volume, or pretty much close to the same volume. A little bit more accurate, 22.414, but for us, 3 significant figures is good enough. And basically, he kept getting the same amount. So the volume of gas, basically, it's independent of the type of gas that you have. Doesn't matter if the gas is molecular or atomic, or even if it was ionic or metallic, if we were to boil mercury, for example. It didn't matter what kind of gas it was. What mattered were the conditions and the amount. So 1 mole of any gas is a volume of 22.4 liters. Okay, this kind of goes back to the molar mass. So the mole kind of is now at the center of this. It's 6.2 or 6.02. It's a no, it's a 0. So I have Avogadro's number between moles and particles.
What does the Na signify?
Avogadro's number.
Oh, sorry.
And then for moles to mass, we use the molar mass from the periodic table. Well, now you go from moles to volume of a gas. at STP, then 1 mole equals 22.4 liters. So from moles to volume for gases, we would multiply times 22.4. From volume to moles, we would divide by 22.4. If we're not at STP, then there's an equation on the next section that we'll have to use. But for now, we make the problems easier by just making sure that we're at STP conditions. And that 22.4 is known as the molar volume of the gas.
What's your next test?
What's today? Tuesday? So this is a Tuesday, Thursday class, so next Thursday. I was gonna say next Wednesday, but we don't think I'll say next week. On Thursday. So it's the last day of class. That will be the last day. Next Thursday is the last day of class. Next week, sometime next week, I will post the final exam on my UPCC.edu for the practice exams. So we have folder that says final exam, and then in there will be a raster file, an Excel file, and it'll have your names, and then A, B, A, B, A, B in terms of exam A, exam B, A, B, A. Just download the exam that you have assigned, and the week after that, then you turn in
On the 11th, right? On the 11th?
Yes. Tuesday, that's a Tuesday, right? Yeah.
Mhm.
Then you just print it the same. So basically, at the end of the semester, you have exam 4 on Thursday, and then turn in your final the following Tuesday.
And you just write it with
Just turning in whatever it is that you're, wait, no, sorry, no, you did that, solutions, electrolytes, I think. Because I am gonna do a crash lecture next Tuesday, or maybe I'll get to part of it this Thursday, on IVs, on solutions. If you need that one. Okay. Because this is a constant right here, 22.4, then there's a direct relationship between moles and volume. If you double the moles, you double the volume. So 2 times 22.4 is twice 22.4. This is 3, then it's 3 times. If it's 4, it's 4 times. And that leads to Avogadro's law, which is V1 over N, which is the same as Charles and Cahuzac's. Relationship. And once again, temperature and pressure, whatever it is, whatever variables that are not part of the equation, we assume those will be constant for the equation to work. At 0.75 moles of helium, gas occupy a volume of 1.5 liters. What is the volume if the number of moles is 1.2? Solving for V2, multiply both sides and say 2. Cancels. should end up with, let's see. Once again, on Pablo's conditions under which he carried out the experiments, atmospheric pressures of 1 and a temperature of 273 Kelvin. So anytime you see that STP, that means that's the temperature and that's the pressure. Those two don't change. That's it. So volumes of gases can be compared at STP, making sure that the temperature is 273 Kelvin, 0 Celsius. And at that point, we can use 22.4 to convert between moles and volume. So we will either multiply by 22.4 or divide by 22.4. So from moles to volume, we multiply. From volume to moles, it's on the bottom, so we're dividing.
Moles to volume, you multiply?
Yes, by 22.4. Then volume to moles, you divide by 22.4. As long as we're at STP.
So is that kind of like a general consensus rule, like it's always going to be most volume you multiply? Is that safe to say?
At STP, it's not a general rule, it is the rule.
The rule, okay.
At STP.
STP. Oh, I keep putting SPT.
You can, the equation that we see in the next section, we can use that when you're not at STP, but you can also use it at STP, but it just adds more calculations.
Yeah. So this would be a good thing to put on the cheat sheet is what I'm wondering.
Yes.
Okay.
Now, the other thing that happens from this relationship is that it extends to chemical reactions. So if we have methane gas reacting with oxygen gas, so it's CO2 and water. So it doesn't work for things that are not gases. So in terms of water here in the liquids, it doesn't work. But this right here is a 1 to 2 mole ratio. For every 1 mole of methane, we need 2 moles of oxygen. Well, because they're gases, this 1 to 2 ratio is also a volume ratio. So if instead of working in moles, we're working in liters. That means for every liter of methane gas that you burn, you need 2 liters of oxygen. And we will make 1 mole of CO2 and 2 moles of water. Well, we know that we will make 1 volume of CO2. Here, we don't know how much volume of water we'll make, because that's in liters. For that, we would have to use the density of water. But the coefficients in the balance equation for the components that are gases, those ratios extend to volumes. And that volume can be liters, gallons, pints, that doesn't matter. The ratio stays the same. So, once again, The volume of the gas is independent of the type of gas that you have. It depends on the conditions. So 1 mole of helium, 1 mole of oxygen, 1 mole of nitrogen. At STP, they will both occupy, excuse me, they will all three occupy 22.4 liters. It doesn't matter that nitrogen is heavier than helium or that oxygen is heavier than nitrogen or oxygen. Okay, the volume will be the same. Now in air, this will float. This will stay kind of floating low, and then the oxygen will move across to the bottom. But their size will be the same. Inside, the masses are different. 4 grams, 32 grams, 28 grams. That's why that one is so today. That one's lighter than air. But their size will be the same. So what is the volume occupied by 2.75 moles of nitrogen gas at STP? Well, just multiply times 22.4, that's it. For an STP, just moles of volume, multiply. Just multiply times 22.4. What is the volume of SCP at 4 grams of meth? Just 3 grams, what's already on your notes. We have the mass, and we want to go to volume. There's not a direct route. Okay, if we had the density of the gas, we could go directly from mass to volume, but we don't. So we have to go to moles. From mass to moles, we divide by the molar mass. From moles to volume, we multiply times 22.4 if we're at SCP, which we are. Molar mass comes from the periodic table. So 4 grams H4. And that's from the periodic table. Yes, you have to look at carbon. Carbon is 12. Look at hydrogen. Hydrogen is 1. 1 times 4 is 4, plus 12 is 16.
Don't you go off, like, when you're using the molar mass, don't you go off how many significant figures that
Yes.
the problem uses?
At least.
Okay.
So that 4.00 has 3.
So then hydrogen would be
Usually.
1.01,
Right.
and then, I don't know what the decimals are, but, okay.
Well, when you look it up on the periodic table, you should use 3 or more.
Okay.
But no less than 1. And then working in reverse, we got the volume, and they're asking us for the grams. From volume to moles, we divide by 22.4, and then from moles to mass, we multiply times the molar mass. 8 liters of helium, Questions?
Can I just ask one dumb question, and I'm pretty sure you said this while I was late. Why are you putting 1 mole of helium twice? I know you're trying to cancel it out, but because you did that up there too. Do you see?
That's, because that's the bridge.
Oh, so 1
So-
and then 2.
So you have to get this, and then once you have this, then we can go to the next one or.
Oh, gotcha.
In reverse.
Okay.
So with experience, then you can combine these two values and kind of skip the moles, but you will have to remember that what ties them together is still the moles.
Oh, okay. Okay.
Because there's 4 grams of helium to 22.4 liters of helium. That relationship, that ratio is only true because they both equal 1 mole. That becomes a bridge.
Okay.
So, from the combined gas law, mole variables. As we take a look at the combined gas law and the different laws, Wells, Charles, Henry, Saxon, and others, there's always a set that's constant. Okay. So that under a certain set of conditions, then the temperature is constant, N is constant, pressure is constant, and volume is constant. So that all of those should equal some constant. But that constant is based on that initial set of conditions. So what becomes that initial set of conditions? Well, since Avogadro did a lot of work on STP conditions and mole volume, then those become the conditions that we will use to calculate what that constant is. So at STP, the pressure is 1 atmosphere. Avogadro measured the volumes of gases to be 22.4 liters. He kept measuring 1 mole of a gas at a temperature of 273 Kelvin. So when we plug all of that in, into that, then we get the value for R. And we're going to call it R. We're going to use the letter R to indicate that constant. So PV over NT is equal to R. Send N and T over to the other side, and we end up with this equation. PV equals nRT. And we call this equation the ideal gas.
The ideal gas law is made, or is using STP conditions. So it's like one factor that can help you convert.
The SCP conditions are built in here.
Okay, are built into R. Okay.
The reason for that is because the whole premise and and we obtain this, we started here. It's that you have an initial set of conditions, but then you can change it. Okay. So once we calculate R, which was that initial set, then these can be anything.
Okay.
So once we have this, then the yield gas law is used when we're not at STP.
Oh, I see, okay.
So we use STP conditions to find R, which allows us to move away
From STP.
from STP.
Okay. And not, but not with like a ton of steps of trying to figure out
Right.
what it is.
And then the word ideal, because experiment and the paper math, they work when the gases are behaving nicely, which they don't always behave nicely. So at the beginning of the chapter, when we had the kinetic molecular theory of gases, just very significant here, but when we had the kinetic theory of gases, then I give you what ideal conditions, experimental conditions would be. We want large volumes, we want high temperatures, and low pressures. So we can do gas experiments with a lot of space, very low pressures, and high temperatures. Then the results we get from the experiment and what we predict on paper using the ideal gas law, they match with gas. If we start moving away from that, if we start putting the gas under a lot of pressure, if we start shrinking the volume, you know, temperatures, then the experimental data you collect doesn't match Higgs particle. And it doesn't mean that the experiment went wrong, or it doesn't mean that the equation went wrong. It means that the gases are not behaving or misbehaving. Basically, they're starting to behave a little bit more like a liquid than a gas. That's what's happening. But it doesn't mean that anything's wrong. So, using more significant figures, the volume, as I mentioned briefly earlier, is more accurate to 22.414. But if we cut that to 3 significant figures, then 0.0821. And that's usually what you will see in chemistry books.
But you can also use millimeters of mercury too, right?
So,
If they ask for it.
with the exception of the denominator of these two right here, temperature has to be in Kelvin, and this has to be in moles. So we don't have a choice on those. These, you do have a choice. Okay. So you can use any unit of pressure, any unit of volume, but as you change those units, then the value of R changes. And it's like working in inches or centimeters. The same distance will have a different number. Right, so 100 centimeters would be 39.4 inches. So 100 versus 39.4, the numbers are different even though they represent the same distance because of the units. So this value when working in liters atmospheres. If we calculate that with other units, millimeters of mercury or torr, then it becomes 62.4. In SI units, which nobody really uses for gas experiments, it's 8.314 pascals cubic meters. So that's another value, but SI. I like to stick to the 0.821, and I just make sure that my volume's in liters and then my pressure's in atmospheres. The textbook though kind of changes the value bar depending on what the pressure is. So if you're given the pressure in millimeters of mercury, then they'll use 62.4. I will convert it to atmospheres and use 0.0821.
I feel like that's too many steps for me, like I would end up messing up numbers.
Yeah, I mean, it does come down to personal choice. And if you remember both numbers or have them on your notes, then the easiest thing is just to use the right one, because you don't have to do a conversion.
Yeah.
It saves you a step. And extra steps means another possibility of making a mistake. But temperature and the amount, we do not have a choice. Temperature has to be in Kelvin. Okay, so pressure is actually what we're looking for. It's a pressure. If we have 0.350 moles of N2O at 22 degrees Celsius in a 5-liter container. And they want the pressure in atmospheres. Okay, so since we're working in atmospheres, then we'll use H2O. Volumes in liters, we're good. The amount is in moles, we're good. Temperature is in Celsius. So we need to convert that into Kelvin. Solving for pressure, divide both sides by the volume, so that it cancels. About 1.7. And as I was mentioning earlier, when we have gases and chemical reactions, for the components that are gases, then the mole ratios will correspond to volume ratios. So we can use the Gill-Gas law equation to determine how much of a gas can be formed, and we know the number of moles, and that mole to mole factor And the balance equation becomes a volume to volume ratio. So, nitrogen gas reacts with hydrogen gas to produce ammonia. Here's the equation. Nitrogen gas reacts with hydrogen gas to make ammonia. How many liters of ammonia can be produced at 0.93 atmosphere and 24 degrees Celsius from a 16-gram sample of nitrogen gas and an excess of hydrogen gas? And there are several ways of doing this. So we have a pressure of 0.93 atmospheres. We want to know what this volume is. We do not have the moles, but we have the mass. And the temperature of So we're looking for the volume of nitrogen. For every liter of nitrogen, we can make 2 liters of ammonia. It's a 1-to-2 ratio, according to the balance equation. So for every 1 mole, we make 2 moles. For every 1 liter, we make 2 liters. So that's why we're looking for the volume here. We find the volume, and we know this volume. Just double it. Okay. Now, we need the moles. So we need to convert to moles. From mass to moles, we divide by the molar mass. And we get that from the periodic table. Nitrogen is 14. 14 times 2 is 28.
Would you not get the more massive NH3? How many liters of NH3 can be produced at 0.93 ATM and 24 degrees Celsius?
But the 16 grams belongs to the
Oh, okay, I see.
to the
JK.
to the nitrogen.
Okay, because you're gonna do the mole factor for the N2 and then NH3, correct?
Yes.
Sorry, disregard.
Well, and do remember, there's more than one way of doing this. Okay, and then I'll, and then the slides will show the other part. But you'll see that it's the same. And that's why the law works. Because, well, that's our school.
Okay.
Get to the same result. So, to 3 significant pairs, that's basically 13 liters of nitrogen. but we're not looking for nitrogen, we're looking for ammonia. And for every liter of nitrogen, we can make 2 liters of ammonia, and that's from the balance equation. For every 1, we can make 2. It's a little bit 30 liters of ammonia. Okay. The other way of doing it is we do this separate on its own. So we have the moles of nitrogen, and then we use the balance equation to get the moles of ammonia. I'll give us like 1.4. And then this, we would plug it in here, but instead of N, it's ammonia. And then when you plug that in here, you get 30. So the way it's here, you get the moles of nitrogen. And then plug that into Q equals nRT.
Yeah, I think that's why I thought that you would do it.
And you can work it either way because the ratio in moles is the same ratio in liters. So if you find the moles of one, you can find the moles of the other one. If you find the liters, you can also find the liters. It's the same ratio. Yes. And then one is not shorter than the other. Okay, you use PV equals nRT and then multiply times 2, or multiply times 2 and then use PV equals nRT. So in this particular case, one route doesn't save us steps versus the other. Okay, but do remember that it only works for gases. Okay, we do the liter to liter, it's only for gases. Okay, this mole to mole, it doesn't matter what they are. This is always true. Gases, liquids, solids. But this is only for gases. One thing that happens here in this last problem is that we had all the hydrogen that was needed. So that in the mixture, we have hydrogen at the beginning, and then there's still hydrogen left over at the end of the process. And that hydrogen is mixed with the ammonia. That doesn't change the properties of ammonia. It doesn't change its pressure. Or its volume or anything. The fact of whether hydrogen is there or not does not change the set of conditions. And that goes back to the kinetic theory of gases. Kinetic gases, we assume that they move in random motion and they are not affected by forces of attraction or repulsion. That means that we consider gas molecules to be independent of each other. So the pressure of any given gas is proportional to the number of collisions of that gas to the walls of its container. How often a gas collides with those walls is independent of whether that gas is by itself or whether it's with other gases. Because the whole premise behind the kinetic theory of gases is that they ignore each other. If there's no forces, then they're ignoring each other. And that's the basis for partial pressures. Okay. That when you have a mixture of gases, then the pressure of that gas is the same whether it's by itself or whether it's in a mixture. Okay, it does not make a difference. The partial pressure of a gas is the pressure that each gas in a mixture would exert if it was by itself. Now, the total pressure changes because that container is now being collided with by two different gases. But the collisions of each individual gas, though, do not change. So, in this example, we have helium at 2 atmospheres in a tank of a given volume. And then we have argon in the same size tank at a pressure 4 atmospheres. So if you empty out one of the gases into the other gas, into the other tank, then the pressure of each gas doesn't change. Helium is still 2, argon is still 4, but the total pressure of the tank has increased. And to find the total, we have to do is add the other two. So we just add the 2 together. The total pressure of a gas mixture is equal to the sum of the partial pressures of those gases. We're just adding them together. Dalton's law of partial pressures indicates that pressure depends on the total number of gas particles, but not the type of particles. The total pressure exerted by gases in a mixture is the sum of the partial pressure of those gases. If we take air as an example of a mixture, air is made up of mostly nitrogen and oxygen. So the total pressure of air is the sum of the partial pressure of nitrogen plus the sum of the partial pressure of oxygen. And this makes up about 99%. The other 1%, then it's smaller amounts of argon, helium, some greenhouse gases, CO2, so yeah. But the bulk is the nitrogen oxygen. If you were to take oxygen out of air, suck it all out, it doesn't do anything to the nitrogen. It doesn't change anything in terms of what nitrogen is. Its pressure would still be the same. Now that total atmospheric pressure, that would change, that would drop. But not nitrogen. So, as an example, if we have 1 mole of nitrogen at STP, then the pressure is 1 atmosphere. If we have a gas mixture of oxygen and helium, then the sum of their moles would be proportional to the sum of the pressures. And basically what this is telling us is 0.4 divided by 1 is 0.4, so this is 40%. So it contributes 40% of this total pressure. 0.6 moles of helium, 0.6 divided by 1, then that's 60%, then helium contributes 60% of that pressure. Okay, so for that example, so in that example, that 1 mole of nitrogen has a total pressure of 1 atmosphere. Well, that means that the pressure of nitrogen is 1. Here we have 0.4 moles of oxygen. That total is 1 mole. That total is 1 pressure. So 0.4 divided by 1 is 0.4. And that's the partial pressure of oxygen. Partial pressure of helium, then is 0.6. So we add those 2, then we get 1. So same thing here, because this is 1, as you do the ratio, 0.5 divided by 1 is 0.5. So it's 0.5 atmospheres. And 0.3 atmospheres for helium and for argon. Then if we add them, 0.5 plus 0.3 plus 0.2, then we get 1, which is what the total is supposed to be. To mention earlier, density of nitrogen, oxygen, in millimeters of mercury. There it is, right there. Okay, these are the ratios. So assuming we're at sea level, or the pressure 760. For nitrogen, we have 594 divided by 760. For oxygen, 160 divided by 760. So that's all. And so that 78% nitrogen in air, that's where it comes from that calculation, that 21% oxygen in air. That's where it comes from. So at sea level, those are the values that we can expect in inspired air. Lower air, that's 100. That's the partial pressure of oxygen. 100 millimeters of mercury. Inspired air, then we have 160. And these are the values.
That makes sense.
That we saw. Over here, 100. And then the 160 here. That's the inspired air. That's that 160. And then you'll notice the 40 for CO2. And then real quick, in expired air. There's always air that just stays in the lungs, or oxygen that stays in the lungs, it doesn't go anywhere. Just goes in and comes out. It doesn't get absorbed by hemoglobin or by the alveoli in the lungs. Basically, it can absorb everything that we breathe in. It only takes a part of it. And so when we exhale, then some of that oxygen that didn't do anything, didn't go anywhere, just goes in and comes back out. Scuba tank contains oxygen with a pressure of 0.50 atmospheres and helium at 55 millimeters of mercury. What is the total pressure, millimeters of mercury in the tank? Temperature constant. So we just need to add the two volumes, but excuse me, the two pressures. But before we add them, we need to match the units. Okay, one is in atmospheres, the other one's in millimeters of mercury. So multiply that times 760. Then once we have in millimeters of mercury, then we can add these two. Get 55 plus something. We get our total. So it's just the sum. The total sum is just the sum of the individual pressures. But we make sure that the units match. If not, change one to the other one. It doesn't matter. We could have changed the 855 to atmospheres and reported the answer in atmospheres. Now, these percentages, for the most part, they stay about the same. And so here in El Paso, we're at about 670. So 21% of 670. So this is atmospheric pressure. And 21% of that here in El Paso is oxygen. That's about 141 millimeters. So, under regular conditions, we pick up 100 out of that 160. Which is 62.5%. So at sea level, the blood picks up about 62% of the oxygen that we have, but that 100 is necessary. Okay, and it works out nicely in terms of having those little clips because we correlate that 100 to 100%. So when you get that pulse ox, that 100 is a percentage, but it's also directly measuring the pressure of oxygen on the energy marker. So that 100% is 100 millimeters mercury. Basically, that's what we're looking at. So it only needs to pick up 62.5% of air. But here in El Paso, to get to the 100, air only has 141. So that's 71%. So this difference in uptake basically has to be made up by red blood cells. So basically people here in El Paso, that's what, 8 points.
Are you saying like we have to work harder to get that oxygen, or?
Your kidneys make more red, or your kidneys like stimulate for you to make more red blood cells in your red bone marrow to compensate for the.
Yeah, so it has to work harder to get.
No, it doesn't really have to work harder. You just have more red blood cells than like somebody at sea level.
Oh.
So we have, on a percentage basis, about 8.5 higher capacity to carry oxygen than somebody who lives at sea level.
That's why if you like go to sea level, you like if you live here most of the time and then go to sea level, you'll feel like 10 times you have so much energy. Like it'll be because you're like the difference between your red blood cell count and other people's, and then you are getting way more oxygen than people who live at sea level normally.
Oh.
Because instead of picking up 100, you're picking up 71% of 160.
And the 8.5 is that percentage, or?
Mm-hmm.
Okay.
You're picking up, instead of taking it about 100, with the amount of red blood cells that we have, we're picking up about 114. So the body now has too much oxygen. So you feel good, and what the lungs do is they slow down. And your heartbeat slows down because it's getting more oxygen. Give it a couple of days, those extra red blood cells,
Yeah,
you get rid of them. And then the opposite, somebody who lives on the beach, they go to high altitude, and it takes them a couple of days because.
When we moved to Arizona, that's what I felt like. Like I was like, I can't like catch my like I felt like I was having a constant panic attack with breath, but not until we studied like respiration.
So what would happen in a higher humidity? What if it's the same sea level but the humidity is
It does one effect.
it won't affect it?
Now, it does affect the total atmospheric pressure. So, once again, this 670, if we look up the weather in El Paso, look up barometric pressure, it won't be 670, it'll be like 7, it will be more than 760 actually, because of humidity. That affects what that total is. So this is what dry air is supposed to be, or around here in El Paso. So the humidity won't, doesn't affect that oxygen contact. Now, it may affect in terms of how your lungs function, if you have asthma or diseases and things of that sort. So there are conditions in which dry air is preferred to high moisture, because the way your lungs are working, that moisture may collect inside the lungs and you may start building up fluid.
Mm-hmm.
But that's not due to the, well, it is due to humidity of the air, but you're collecting it because there's something wrong with you.
Yeah,
Not something wrong with the atmosphere.
Yeah, getcha.
There's a systemic issue. I can't really say. Now, the bigger the difference, then the longer it'll take for you to acclimate. So if you're going to higher altitudes, the bigger the difference that you're going, the longer in terms of days. So if you decide that you want to go climb Mount Everest,
You'll
then
die.
it's not a couple of days, but you're talking 3-4 months. So only rich people or people who don't have a lot to do it can afford.
Yeah.
Because before you even attempt to climb,
You have to
live
acclimate.
in the area for about 4 months.
yeah.
So it's not like, hey, next year, let's go climb. Like, you have time to go and live.
For a few months.
And even then, you may say,